Good morning. I'm Saurabh Sinha. I work in the Research and Development Group in ARM, Austin, Texas office. Before I begin, I'd like to thank the organizers of this workshop and the SISPAD committee for giving me this opportunity to stand amongst industry and academic experts to talk about digital design. And I'll concentrate on the value of early stage design technological optimization. So this is a brief outline of my presentation today. I'll begin with an introduction, look into digital design with the standard cells as the main highlighting point. Look at the impact of technology on design, especially the transition to FinFETs. And finally, I'll present some early research results that we have been doing in the ARM R&D group. That's the value of design technology optimization. We've been doing some predictive technology models and some implementation work. So everyone's aware of Moore's law, and this is just another way of showing how different technological advancements are going on, trying to extend Moore's law, trying to continue the scaling. We started off with planar CMOS, single patterning, copper interconnects with local interconnects coming in. And if we start giving node names here, you'll see at 20 nanometer we have double patterning with planar transistors, moving quickly to FinFETs at 14. And then as we go ahead, plotting just complexity versus time, we see that the complexity starts to multiply increasingly, and things start to become really, really difficult to actually implement. There are many different technology options in terms of interconnects, patterning, and transistors. And as a fabless design IP company, what ARM likes to do is look forward into the future and figure out what different technology choices we have for doing design and how to optimally use them. Now in this slide, I'm just highlighting the transistor technologies, and as you can clearly see, we can quickly move on to very exotic devices in the next few years. And the big question that we're trying to answer is, how do we design with these devices? And you might be an expert in, say, FinFETs or 3.5 devices. You're doing a lot of TCAD simulations. And my goal today, through this talk, is to tell you how designers use these devices, and under what conditions and context. Because a lot of times, the answers that the designers are looking for are different from what is published in research results, what is being simulated, and what results are being shown by technology researchers. Now, it's very important for designers to look into these exotic devices. They're really interested. But there's a gap between what kind of research is done and what results are published and what we're looking for. So, and the big question, again, so yeah, this is just a cartoon which shows the different device options. And the big question is, how do we evaluate the merits of these technology choices and the trade-offs involved to optimize design? So for that, let's take a short detour into digital design, and I'll be mainly concentrating on standard cells. So what's in an SoC? In a modern SoC, you have about 20% of analog and I/O circuits, 40% logic, and 40% memory. Now, 40% memory is a bit too high, but it's convenient for this talk. And since we have a couple of excellent talks lined up for analog and SRAM design, I'll be mainly concentrating on logic. And to understand logic is to understand what is known as synthesis, place, and route, or SPNR. So very briefly, what SPNR does is, we have a piece of design architecture. We identify, say, one part, and the synthesis tool will create a netlist or a circuit based on what are known as standard cells. So here, I'm showing a very common component, a full 4-bit full adder. And what the synthesis tool does is, based on the design constraints that are given for timing, area, power, it will try to identify the best circuit components from your standard cell library and put them together. And here, this is basically the circuit netlist. And you can see the main gates involved here that's shown through the lines here. So once the synthesis tool has identified the basic standard cells to put in together, the placement tool comes in and starts placing these cells vertically or horizontally, mirroring them. And they can be placed at any gate pitch, basically. And finally, the router comes in and wires them up together to form the final circuit. So that's briefly SPNR in a nutshell. Of course, the actual implementation and optimization is much more complicated and involved, and we'll look into that soon. So what exactly is a standard cell? It's basically an NFET and PFET, basically the complementary MOS gate, the gates that you form. But the thing that makes it standardized is that it's generally an integer multiple of the gate pitches and integer multiple of the metal tracks, or minimum metal tracks. So this cell here is 3 contacted poly pitches wide, 3 CPP, and it's 8 minimum metal pitch tall. And each metal pitch, in minimum metal pitch, is called track. So this cell is 8 tracks tall and 3 poly pitches wide. Now the main thing to remember here, the other constraint is that the height of the standard cell remains constant for a given track library. So if you say I have an 8-track standard cell library, all the cells in the library will have exactly, the height will be limited to 8 tracks. So you won't change the height. And you can go for a different height metal track library as well. So you have the top and bottom metal rails as VDD and VSS power rails, and then you use the intermediate region to connect the FETs together to form the final gate. In this case, we have the input pin as A, output pin as Y, and this is generally done in metal 1 or the local interconnects, depending on which technology node you're looking at. And finally, the metal 2, which is a higher metal track, basically comes in and tries to connect these different cells together. Now, depending on how many intersection points you have between the pin and the metal 2 router wires, they are called the hit points. That is basically where it's going to put in a via and contact to your actual circuit. Now, for example, here there are 5 hit points, and if you consider the Y pin, and for the input pin there are 2 hit points. If you allow your metal 2 router to go in, drop to a lower metal level, and then connect again, you can have, in this case, up to 4 hit points. Now, the basic rule of thumb is if you have 3 hit points, you're just OK. 2 hit points is good only in moderation. And if you have just 1 hit point, then that's basically a recipe for disaster. Now, the main reason being, once you start placing hundreds and hundreds of these cells together, the wires start to go really crazy. And they need to find the more number of hit points that you have, it's better for implementation. If you have less number of hit points, what happens is the router starts to get vexed up. What it'll do is it'll start placing the cells away from each other, not very close by, so that it can have the wires to route through. And the area of your total chip will start to increase in spite of the amazing transistor technology or amazing patterning technology that you're employing to get a better area and density. So that's one of the important parts of standard cell synthesis, place, and route that you need to keep in mind, is that you need to have enough number of hit points so that the router can place the cells together close enough. All right. So as I mentioned earlier, standard cell height is restricted, so you cannot have more than, so once you fix the standard cell metal track height, you do not increase the height. So how do you increase the strength of your transistors? Basically, how do you increase the widths? So for that, what you do is called folding the transistor. Here, there are 2 gate fingers per FET. Which is the laser? Yeah. So here you have 2 gate fingers for this one FET, and basically this cell is called a 2x strength inverter. So as you want more drive strength, you basically start increasing the width, not the width of the transistor, but horizontally you start adding more and more folds here, and that's how you get multiple drive strengths. So that's another important part of doing a standard cell library design, that you need to size the gates accordingly, and you need to have multiple variants of the same gate with different drive strengths. So for example, in this picture here, what is shown is a NAND, 2-input NAND gate. And as you can clearly see, there are multiple variants of this NAND cell. This is an X1 strength, this is X6, and here it's an X5. So basically 5 times the drive strength. And you need to optimize your library for different drive strengths. And as you increase the drive strength, basically the width in tracks of the horizontal tracks, the metal pitch tracks, start increasing. And your area increases, and you need to optimize the capacitance as well, because as you're increasing the drive strength, you're adding more FETs, you have more input capacitance. So if you look at a standard cell library for a single gate, for example, in 2-input NAND, you can have up to 60 different embodiments of the same cell, but with different drive strengths to match the timing criteria. The synthesis tool will pick up the right gate to meet the timing constraints. And synthesis tools are far more efficient as well, because if you do not have the right rise time or fall time, it can pick up a cell with different beta ratio, that is the ratio of the N and P drive strengths, and put it in place to meet the design goals. So basically, your standard cell library now has a lot of different gates. Some implement Boolean logics like inverter, NAND, NORs, and or invert, or and invert. Complex cells like flip-flops, multiplexers, and then clock-based cells. And about 60 to 70% of your critical path utilizes these Boolean logics cells, and the area is mainly dominated by flip-flops. And generally, your standard cell library will have a permutation of different beta ratios, that is the N and P ratio, different drive strengths, and different threshold implants. And about 1,300 to 1,500 cells is pretty common for a standard cell library. And this is per cell height variant. So here, for example, I'm just looking at 8-track standard cell library. As you move to a different track height, you can have, again, these different number of standard cells in that library. So which size is best? Well, you can design, say, a 7-track, a 9-track, or a 12-track. But what you need to keep in mind is that the white space, that is where you cannot have transistors, basically to have the metals, the power and ground metal layers, and basically the contact region between the NFET and PFET, that white space is the same if you look at a 12-track height library or a 7-track library. So basically, the amount of space you have for your active transistors gets limited as you go down to a smaller metal track. So but we do need the smallest possible and the fastest possible library, which is contrasting. But that's where designers come in and try to optimize the design within track standard cell library. And most SoCs use a mix of 2 or more different cell heights. So with that in mind, just try to look into the future of how the standard cell libraries will look in the future. Here, what I've done is taken the ITRS roadmap from 2012 to 2020. And ITRS is convenient for future projections, but the industry trend will be definitely less aggressive. And here is the metal pitch predictions, which go from 64 nanometers all the way to 24 nanometers in 2020. And if you consider that you lose the power rail metal pitch and the 2 metal pitches for the power rails and about 2 metal pitches because of restricted design rules between the PFET and NFET, the amount of FET area that you have, total FET area, that's an NMOS and PMOS, you can see that it's pretty limited for a 1x drive strength. So as you increase the drive strength, you put in FETs in parallel, but the maximum width that you draw for an NFET and PFET combined starts with 320 nanometers and goes all the way to 120. So basically, just for your NFET, you have about 160 nanometers of gate width that you can have. Now, if you're considering FinFETs, the number of fins that you can fit in a 9-track library would be about 3 to 4. So that's the basic assumption here. So the maximum device width is limited. You fold the transistors, but the width that you draw is actually about 160 nanometers, or about 4 fins. And that's a very important result, because it's an important observation, because most of the device-related research papers that come out will show you a device which is 1 micron wide. It is the minimum length transistor, but it's 1 micron wide. But what designers really need to see are very small width devices, because that's what they're going to put in. And this is true for digital design. I'm not talking about about analog design here. But for standard cells and digital design, it's very important to see very small width devices and what the different effects and the second order effects that come around while doing these small devices. And then comes design sign-off. So once you have the whole standard cell library, you implement your design. It has to be signed off at multiple PVT corners. So you have different process corners, like typical fast, slow. You have global and local corners. There are wire corners these days where you have worst case RC. You also have worst case coupling corners because of double patterning. So if you do not have overlay between the 2 different colors of metals, because of overlay errors, you can have higher coupling in some cases, and that corner is also an additional point where you need to sign off your design at. You have numerous voltage corners and then temperature corners. And the worst case combinations for performance, active power and leakage power are considered while doing the final sign off. And that's again another important point where future device research needs to take into account these conditions. So we need numbers at slow corners or get some idea of variation. We understand that most of the future device research that is being done, you don't know a lot of details, but when you're doing some kind of simulation, it's important to see how it behaves across temperature and report those results, because that's where designers are really interested in. So in summary, coming to the end of this section, a standard cell library can have different unique topologies and thousands of cells in them, depending on drive strengths, beta ratios, and different cell heights. They must abut arbitrarily to one another and can be mirrored and offset. There are a lot of different layout solutions to get to the optimized result. Pin accessibility matters a lot. And for any device research related to digital design, it's very important to have density and performance optimized for typical 9-track or 12-track compatible device sizes. And we need to know variation, voltage, and temperature behavior, and not just typical 25C values. So with that, I move to the next section. That's the impact of technology and design. Here I'm trying to show the impact, how scaling has changed a lot of things after the 90-nanometer technology node. Well, conventional scaling, we're looking at the saturation current equation here for a typical MOSFET. Conventional scaling used channel length, gate oxide thickness, VDD, threshold voltage, doping to scale these transistors down. But that was the short channel effect started limiting them. Moved to strained silicon to get increase in mobility. To control gate leakage, we moved to high-K metal gates. And then finally, at 22 nanometer, FinFETs were introduced, basically, which improves short channel effects, allows VDD threshold voltage scaling, increases the effective width, depending on what height of the fin you have and what's the fin pitch. But this involves a lot of process complexity and design implications. So just to give an idea of some of the effects that have come across due to all of these different materials enhancements, structural enhancements, we're looking here at layout-dependent effects. The result is from a sub-40 nanometer test chip, and this shows normalized ring oscillator frequency across different oscillators. And these are local reference ring oscillator instances. Here we're looking at channel length modulation. That's basically just changing the channel length. Obviously, the frequency goes down as you increase your length. Well proximity effects. An interesting side effect of gate pitch modulation, because of different strain effects, what we've seen is that increasing the gate pitch can enhance the frequency or improve performance. Now, that comes at an area cost, but you need to take into consideration all these different effects while doing your standard cell library design. And if variable gate pitch is allowed by the fabs, you can probably take advantage of this feature. Then the big limiting region is the lithography challenge. How do you reduce the feature size of these transistors? How do you print them? And that has a lot of design implications as well. So here, what you draw basically is not what you get. There are rounding effects. There are a lot of other effects. And in this plot here, it shows the wavelength of light used across in the last 2 decades, and the reduction in feature sizes. And as you can clearly see, the wavelength of light has been pretty much constant in the last decade at 193 nanometer, and that's mainly because of economic viability. EUV is just around the corner, and it's been like that for the last few years, and we're not really sure at which technology node EUV is going to be introduced. But with current 193 nanometer lithography, there are numerous different methodologies applied by lithographers to keep on reducing these feature sizes. And these include increasing the numerical aperture, decreasing K1, using resolution enhancement techniques. And finally, the big the game changer, that's basically multiple patterning, because this has a lot of design implications again. So coming back to standard cells, the logic should scale as contacted poly pitch and metal pitch, because basically what you're doing is if you have a 9-track library at a given node and you move to the next node, you can keep the same track library, and because the metal pitch scales and the contacted poly pitch scales, you get a reduction in area. Your transistors are getting better, so you get improvement in performance. So that's how technology numbers are still advertised. However, logic scaling is far more complicated. And as an example, here is a 65nm flip-flop. It has great gate density. It has a lot of jumbled layout, and each of these different constructs here have their own advantages. For example, you have diffusion tabs, which can get power directly from the power rails. Contacted poly pitch is not limiting anything. So you have 3 independent transistor contacts in the same poly pitch. There are horizontal PC routes, that's the gate routing. So the gate polysilicon can be routed to contact 2 different gates on the outer side of metal rails. And uneven gate pitch is allowed. And then you have minimum metal 1 tip to side spacing in a lot of places. Now, these tricks are not legal anymore as you scale down to below 65 nanometer, because diffusion tabs are lost. There are rounding effects of lithography, and you need consistent patterning, which is a requirement, and you have double patterning cut masks, which do not allow you to do all these different tricks. And the fixes for these have a cost, and this typically involves either making the cell wider or adding metal 2 to the cells, or both. So this is a scaled node. It's an example high-K metal gate flip-flop. And what we've seen is that the number of metal pitches, number of contacted poly pitches that was required for the 65 nanometer flop, the number of poly pitches required at this scale node increased, which increases area because of regular layout. Also, you cannot just have metal 2 to route the internally within the cell. We needed metal 2 as well. And this basically adds local route congestion because it increases the block area further. So once you have metal 2 inside your cell, the router metal 2 cannot use these 3 tracks. So that increases routing complexity. And since you need dummy gates at the ends, that increases the area by about 20%. So you are actually scaling down, but in some of your circuits, to meet the timing criteria and to meet the routing requirements, you have an increase in area as well. So notice that with scaling, everything is much more regular now. Layout freedom is restricted. What you see is not really what you get. There are minor tweaks involved. And finally, the area scaling is non-ideal. The average density is often less than the peak density, but that's not really the case everywhere, but in a lot of places, and depending on what kind of cell you're using and what kind of circuits you're looking at. So now we come to the big transition, that's FinFETs. I'm pretty sure everyone here is familiar with FinFETs, but the big difference to designers is instead of having a variable gate width where you can vary it by any number, your gate width can only be changed in number of fins. So you can have a single fin, 2 fins, 3 fins, but it's an integer multiple of the fins. So you cannot have an arbitrary gate width value. And the other big change was, since it's a 3D profile here, the effective width is the 2 times the height of the fin and the thickness of the fin. And if that is more than the fin pitch, you have what is we call the 3D factor, as the additional gate width within the same planar area. And that also has implications in design. So basically, you contact the source drain regions, and if you look at them from a top view, it basically looks very similar to a planar transistor, where the only difference being, in the planar transistor, you could change the width by any value you want, but here you have to you can only increase by 1 fin pitch, or 1 fin. And the advantages are you have better ion versus I-off scaling, near ideal subthreshold slope, reduced or eliminated random dopant fluctuation because you're not doping the fins, lower dibble, and reduced body effect. So coming back to standard cells, here the assumption is that we have a 48 nanometer metal pitch. This is for a scaled node. And if you have a 9-track metal pitch, now you have to take into consideration that the fins have pitches as well. So how many fins can you fit within the 9-track standard cell library. And that tells you what limitations you have in optimizing your design. For example, if you assume that 2 fin pitches are lost on the top and bottom, and 1 fin pitch here, basically what you have is 3 fins per NFET and PFET. So that comes to the fin pitch selection issue. Designers and the fabs need to collaborate early on to figure out what fin pitch is to be used, and how many transistors or how many fins can you have in a single FET. So when it says 2, it means 2 fins per NFET and PFET. And what is the track height, the metal track height here. So going from 7-track library to a 12-track library, and what the fin pitch will be is filled up in this table. Now the obvious choice is having the same fin pitch as the metal pitch, but to reduce the dead space capacitance and improve CV over I metrics, there is an incentive for going for reduced fin pitch. But that is also limited by lithography limitations, the issue of fin merging, increased contact resistances, and there are a lot of issues to be taken into consideration. But what basically tells you is that the maximum number of devices that you can, the maximum number of fins you can have per device would be generally limited to about 4 or 3 fins per FET in a standard cell library. Now, the other interesting issue is the issue of the 3D factor, where the effective fin width is much more than the fin pitch. What that results in is within the same planar area, you have more effective device width, which gives you more drive current, but at the same time, you have additional capacitance as well. So you need to optimize that carefully. So looking here, what we plotted is the NFET and PFET width for a 9-track standard cell library and normalized to 40-nanometer node. And as you can see, for planar transistor, it had been scaling pretty much consistently across the technology nodes. And as you go from 20 to 14, if you do not change the metal pitch, basically your metal track height remains the same, the effective width that you get within the same cell is more than what you would have got at the 20-nanometer node. So basically, you have more drive strength, more capacitance, and hence you need to optimize your library accordingly. So these are for a 4 fin per FET projections, and this is 3 fins per FET. So in your standard cell library, you just have 3 fins, not 4, per NFET and PFET. So what are the design impacts? Well, you have fewer cell variants because of width quantization. So if you have 3 fins per FET, as say for beta ratio, you can have 2, 3, or 3, 2. And that's basically the most you can get out of it, or 1, 3, and 3, 1. The VTH and gate length options have reduced. There is stack effect, that is, there is reduced body effect coefficient. So that has an impact on stack delay and impact on leakage. Variability is the big question here. What are the different variation signatures that you're going to get with FinFETs? And then temperature dependence. So variability. Now, the main advantage that has been published a lot is that there will be less random dopant fluctuation because the fins are not being doped. So local variability might reduce, but then there are new variation signatures such as the fin line edge roughness and source and resistance variation. Gate work function variation is another major source. So there is a possibility of shift between the local and global variation balance. There might be possible improvement in device tracking. And here I've shown some recent research results looking at variation in FinFETs. The other big issue is temperature dependence. Now at sub 65-nanometer nodes, what we've been seeing is across threshold voltages, for different threshold voltages, the temperature, worst case temperature corner changes between the different VTs. And that's mainly because it depends on the VDD minus VT and the mobility trends for across temperature. And as you can clearly see, and this is for a planar transistor, these two VTs, VT1 and VT2 at VDD nominal have the lower temperature as a slow corner, while as you decrease your VT threshold voltages, you go to a lower VT transistor, the worst case corner is basically the higher temperature. And the same thing across different voltages for the same VT, you can see that the worst case temperature corner changes as you change your VD threshold supply voltage. This basically complicates device tracking behavior and complicates multi-VT and DVFS use. So that's another important thing that we need to take into consideration while designing with FinFETs is, do they still have the same temperature behavior, or does it change? And that's, again, my message to all the device researchers is to give us data across temperatures and not just at the typical one. The other implication would be the body effect. Since FinFETs have very reduced or negligible body effect, what we've done here is we have taken a planar transistor model and just changed the body effect coefficient and tried to see how does that impact NAND 3 and a NAND 4. So how does the delay change? And we're looking at the different inputs, A, B, and C, with A being the closest to the output. And what we've seen is, compared to a typical planar transistor, which is somewhere here, if you have nearly zero body effect, basically you can have a NAND 4 delay similar to a NAND 3 delay. So basically you can have a higher stack height and get similar delays. So that, again, has a big impact on design. So with showing all these different effects, the big question is, which library design enables the best power, performance, and area at a given technology node? So, for example, I have a technology option of FinFET coming in with multiple patterning. And how do I design my standard cell library? And I have to take into consideration all of these different effects: fin dimension choices, layout-dependent effects, strain, parasitic capacitance, increasing source drain resistance, gate and source drain contacting, restrictive design rules from foundries, wire congestion because of routing issues, increased wire RC, and I did not talk about interconnect issues, but that's another a big roadblock right now, variation, reliability, and a lot more. And the answer is, you cannot know the correct answer without using the library in real design, and a lot of iterations are required. So to get to this answer, what we think is important is early stage design technology co-optimization. So the questions we're trying to answer is, how do current cores and architectures behave at future technologies? How do we create the cores and architectures of the future with so much uncertainty? And the answer is early DTCO. And what we've done is, since we have our own core IP, we have our own physical IP, we decided to do an internal PDK, run standard synthesis, place, and route, and get power, performance, area numbers. And the main target is to get our predictions ahead of foundry PDKs, because the foundry PDKs come in quite early, actually, before the design goes into production, probably 2 or 3 years in advance. But we also need to look at some technologies which are further ahead, probably 5 or 6 years in advance. And to do that, the best thing to do was to do our own stuff. So as a starting point, we developed some early FinFET models. And these were aligned to the ITRS technology nodes. And these are available on the ASU website that can be downloaded. We have 2 versions aligned to the ITRS roadmap, the high performance and low standby power LSTP models. We published a couple of papers which discuss the results for these models at DAC and ISLPD 2012. Basically, we have these LSTP models here, HP models across different years. And the assumptions are based on whatever ITRS is assuming for these technology nodes. The ISLPD paper looks at the delay versus supply voltage, delay versus energy studies based on very simple ring oscillators and figure of metric circuits. Now, all these models are based on BISM CMG, which is developed by UC Berkeley. These have very simple assumptions on back-end of line RC. There are delay, power, and energy trends. But still, this is limited because all the complexities of contemporary design cannot be captured using just simple transistor models. So what we've been doing is, within R&D, we have what we're calling the ARM PDK, where we have the electrical models based on BISM CMG. Now, these are different from the public models because we have internal information based on which we decide how to set up the transistor targets. We have DRC, LVS, basically that's the design rule checker, layout versus schematic checker. And what we've been again working on is extraction, which is a big component to get the parasitics out. This uses the interconnect technology format, which is an open source format. It's a standard. And TechLeft and LeftDef standards, this is basically for routing the higher metal layers. And this is used by the router to accurately route across the standard cells. We are taking into consideration a lot of effects like multi-VT, variation, temperature dependence, handling multiple colors for double patterning, and lithography dependencies as well. So with that, we have a standard cell library for 14 and 10 nanometer nodes. And here are some predictive implementation studies that we've been doing. This is an ARM Cortex M3, a microcontroller, which does not use memory. So this is using just standard cells. And what we show here is normalized total power versus normalized frequency for different technology nodes, 28, 20, 14, and 10. Here is normalized efficiency versus frequency. And this basically tells us or confirms how things will behave on actual implementation. So you can get a trend from simple CV over I metrics, which show that, okay, you get a 20% improvement in performance or this much improvement in power, but that's based only on ring oscillator simulations or simple figure of metrics simulations. But this gives us numbers from an actual implementation. In addition to just doing scaling predictions, we can do architecture analysis, which is in more pertinent environments. And we can do cost trade-off analysis to support DTCO. For example, a lot of research is going on reducing the back-end of line parasitics, reduction in resistances. A lot of research is going on to improve the mobility of these transistors. And we have the ability to do cost-benefit studies of these in-research technology options. And as an example, this is mobility enhancement cost-benefit study at 10 nanometers. So what we've done is taken basic BSIM-CMG models with base nominal mobility, increase the low field mobility. So these are different caveats in the actual implementation, but we're just looking at the low field mobility parameter, increase it by 30%, increase it by 60%, and see what happens to the standard cell. How does the synthesis place and route tool pick up these cells and implements the final design? So what happens basically here, you see the normalized total power trend, and from the base, that the power goes up initially, but for the 60% higher mobility standard cell library, it goes down. So basically, that's telling us that the synthesis tool is picking up smaller cells now, and that reduces the total power, but still achieves improved frequency. And this gives us a good way to plug in different technology options into the whole flow and see what comes out at the other end. And we understand that the total PDK is not complete as we get from the foundries, but it gives us a good estimate of what things will look like. And we can keep on adding different technology options, improving the models so that we get closer to the right answer. And more often, it's the trend that matters rather than the actual absolute numbers. So with that, I would like to come to a summary of my talk. To evaluate any technology, it's important to examine all design rules, how they interact with physical IP instances and implementation flow, especially for scaled nodes. The answer is always it depends on the circuit, on the targets, on the applications. We might be tempted to infer too much from simple ring oscillator simulation results, but the real answer is always more complex and statistical. The real answer requires routing and block level metrics. And designers really need relevant transistor metrics from technology researchers for any kind of evaluation, for useful evaluation. And detailed DTCO can help tune the solution for optimum benefit. And the predictive PDK and the implementation that we are doing is an effort to get ahead of this DTCO curve and evaluate these technology choices. Before I end, I would like to thank the R&D team at Austin and San Jose, Greg Eric, Brian Klein, Rob Aiken, Vikas Chandra, and Lucian Schifrin, and Professor Kevin Chow and the PTM group at ASU for hosting and maintaining the PTM models. And thank you.